Alright, so now we're looking at molecular compounds. Okay, molecular compounds are formed by different atoms than ionic compounds, and the way that they bond is different as well. So with molecular compounds, it is a compound formed when atoms of non-metals combine. Okay, so just off the top though, you see molecular compounds here. The bond that happens between them is a covalent bond, and sometimes they're called covalent compounds. Okay, so just know that that term is kind of intermingled. Molecular and covalent kind of mean the same thing. All right, so people use those two terms for the same topic. Okay, so properties of molecular compounds. So we went over the properties of the ionic. So properties of molecular, they can be liquid, they can be solid, liquid, or gas compounds. These ones have low melting and boiling points, but as remember the ionic compounds, they had very high melting and boiling points, so the heat had to be extreme for them to melt or boil, whereas with these ones, very low. So for example, water is a molecule, so it's a molecular compound, and it boils at a very low temperature. Okay, so these ones are poor electrical conductors, obviously, because in this case, there's no metals involved, right? These are just non-metals, which is why they are poor conductors. And many of these are not soluble in water, so they don't dissolve in water. So, as I mentioned before, molecular compounds are also called covalent compounds. Their bond is a covalent bond. They share electrons and are usually composed of two or more non-metallic elements. The combining capacity of a nonmetal is a measure of the number of covalent bonds that it will need to form a stable molecule, so full outside shell. So the whole thing, the molecular compounds, it's the same as the ionic, where you have these atoms that want to have a full outer shell, right? Just like those noble gases, who have full outer shells, and therefore they don't need to make compounds. They don't need any electrons. They don't need to give away any electrons. So these guys still want that full outer shell. But the difference is, I'm just going to show you an example here. Instead of, we had sodium and chlorine, which makes sodium chloride. Instead of these guys, giving away, where sodium would give away the electron, and then all of a sudden now chlorine is that negative charge and sodium's that +1 charge. And then because of those charges, they're attracted to each other and they come together and form a compound. Molecular compounds, there's no giving or taking of electrons, okay? These guys are always sharing them. So with an example like H2O, your water, you have your oxygen, which has 6 electrons. And actually, I'm just going to do it differently here, how they would actually bond. Hydrogen will come in with 1 electron here. Another hydrogen will come in with another electron here. And what they do is they end up sharing a set of electrons. So hydrogen will share. So what happens is these electrons will circulate back and forth between oxygen and hydrogen. And these ones will circulate back and forth between that oxygen and hydrogen. So at one point, hydrogen will have both of these electrons and be full. And at another point, this oxygen will have both these electrons and be full. So they're sharing them. They never give up, or they never take. And this is because of nonmetals. So looking at the periodic table, by working, I'm just going to pull this out here, by what we've done with the ionic compounds, you've gotten familiar with the fact that these guys over here, the metals, they tend to give up their electrons, right? These guys all have 1 in their outer shell and they give them up. These guys all have 2 in their outer shell and they give them up. These guys have 3 and they give them up. So the metals tend to give up their electrons, and that's just because as you get to this corner of the periodic table, this corner, they have a very loose hold on their electrons. So these guys are more likely to lose them because they don't have a strong electron affinity. Like their hold on them is very weak. But as we go towards the other end of the periodic table, where the nonmetals are, these guys have such a strong hold. So this is when they form ionic compounds. These guys up here, these guys are the ones that are gaining the electrons because they will not part with their electrons. They have a firm hold. So looking at molecular compounds, which are only made with nonmetals, which is these guys here, well, none of these guys are going to give each other electrons. They all have a firm hold on them, which is why they share them, okay? They end up sharing them because none of these guys want to lose any of their electrons because they have such a strong electron affinity, which means that they have such a strong hold. They won't give them up. So when they're sharing them together, they're not giving them. So when the two of them come together, like your hydrogen and oxygen to form water, they both want to hold on to the electrons, but they're willing to share them. So what happens is the electrons just float back and forth. Okay, so no one ever really holds on to them. So just so you know, remember, these guys never, ever, ever have a charge. Molecular compounds will never have a charge. They're never at a point where they're actually losing or gaining their electrons. There will be no charge, okay? All right, I'm not sure where I left off there because my camera got a little funny. But back onto this page, okay, we're talking about the bonding, okay? So we're looking at how the bonds are different from ionic compounds to molecular compounds, okay? So with ionic, they were giving and losing electrons, and as I said here, they're sharing them, okay? So when we're dealing with molecules, which is molecular compounds, okay, they're molecules. And the difference between the molecules than the ionic compounds, which are known as salts, remember I talked about the Legos and how you can keep building on to the ionic compounds as long as you keep the ratios the same. Molecules, you cannot build onto them. It is a structure and it cannot be penetrated by anything else. And as soon as you add something into it, the molecule itself will change, okay? Sorry, my computer's battery is starting to die, but it should be okay for a little bit. All right, so we have an example here with the carbon and hydrogen atoms, all right? So we have a carbon, which has the 4 electrons in the outer shell, right? And they don't give them up, they don't lose them, we're willing to share them. So hydrogen comes along, and you can see hydrogen will give 1 electron because that's all it has to give, as long as carbon gives hydrogen 1. So in that case then, there's a set of 2, and those 2 are being shared back and forth, okay? That is referred to as a single bond, okay? Equals 2 electrons being shared, okay? So that's 2 going back and forth, okay? So carbon has single bonds here with all of these hydrogens, okay? Single bond is 2 electrons being shared. I'm going to show you something else. You can have double bonds, which would be 4 electrons total, okay? So in that case, I'm going to show you just something off to the side here. Carbon could share 2. Nope. I was going to show with hydrogen, but that's okay. So carbon can share 2, and we can say, let me see here, oxygen, because oxygen needs 2. All right? So oxygen will give 2 to carbon, carbon will give 2 to oxygen. Okay? So in that case, when oxygen has the 2 from carbon, then oxygen would be full. All right? So there's the total of 8. And that would be 4 electrons total being shared, which means it's a double bond. Okay? And see how single bonds are represented by 1 line, double bonds are represented by 2. Okay? But carbon will only be getting 2 electrons from oxygen, which would mean it would still need, then it would be full, okay? So carbon has 4 there. So oxygen has 6, it would be getting 2 from carbon. Carbon has 4, it would be getting 2 from oxygen, which would mean it would need another oxygen, right? So then at one point, it would have it would have the 4 electrons here, and it would have the 4 electrons here, okay? And it would be full, and then at one point the electrons would go over to the oxygen, and that would be full. So this would be showing, that's showing 2 double bonds, which means 4 electrons going back and forth, right? So there's 4 here, so carbon would have 8, and then oxygen would each have its 8 on the opposite sides, okay? And then a triple bond is the last one, triple bond, and that would be 6 electrons being shared, okay? Okay, so molecule, not like ionic compound, there's no ratio, okay? It's structure and it stays the same, and as soon as you add something into it, then the molecule itself changes, okay? The naming with molecular compounds is a lot easier, I feel like, than ionic compounds because you don't have to look for the charges. You don't have to try to figure the charges out first. The naming is given to you. The only thing that you do have to remember is the prefixes, okay, and what they represent. So I've given you a list. I've added on 2 extra ones. We don't usually see hexa or hepta very often, but I thought I would give them to you anyways. Mono is 1. You have your di, which is 2. Tri, which is 3. Tetra, which is 4, and then your penta, which is 5. And then I gave you hexa 6, hepta 7. We don't usually use those very often. Okay, so things that you have to memorize are the prefixes for the different number, which represents how many of the atom is in that molecule. Okay, so we're going to do some examples with you. All right, so let's do some examples. Just some notes, though. With ionic compounds, remember you didn't have to write down the 1, okay? Molecular compounds are sort of like that, but only with the first one. So, when the first one, all right, and it's usually whatever non-metal is the furthest left on the periodic table, that's the one you write down first. But everything has a prefix, except for when the first non-metal is just 1, then you don't write the mono for it. So in this case, carbon monoxide, all right? Carbon monoxide is just a C and an O, right? Instead of saying monocarbon monoxide, we just say carbon monoxide. So whenever the first non-metal is just 1, we don't write mono. Okay, we don't write the mono. You would write anything else except for that. And like I said, you know, chemists like to find ways to be lazy. That's one of the things. So whenever the first nonmetal is just 1, we don't write the mono for that one. Okay? The O is dropped from mono when the second element is oxygen. So it's not monoxide, it's monoxide. Right? And then the A is dropped from tetra and penta. So when it's oxygen, right? Because it starts with an O. So it's tetroxide, not tetraoxide. So that's another point there. So let's go through the rules. So same as ionic compounds, the name of the molecular compound ends in id, like ide. You know, like for the ionic compounds, it was sodium chloride. You still have to use the ide on the ends of the second nonmetal. Name and formula usually begin with the element that is more to the left of the periodic table, right? So whatever's on the furthest on the left, that's when you write down first. In the name, use the prefix to specify the number of atoms of each element, okay? So this is great because then you don't have to worry about trying to find the ionic charges for anything because these guys never have a charge. So more common molecular compounds do not use the set of naming rules because they already have common names. We're not going to worry too much about these because we're not in class to commonly use them often. Though H2O is one that everyone should know. It's water. It's not dihydrogen oxide. H2O2, though I guess most people probably don't understand what hydrogen peroxide, what the chemical formula is, but that is hydrogen peroxide. And we use Per, and we're not going to worry about this too much now, per is added onto oxide because it just means an extra oxygen when it's named after something right after water, like that. So per actually stands for extra, but we're not getting too much into that. Instead of dihydrogen dioxide. And then ammonium is NH3 instead of nitrogen trihydride. But again, we're not looking too much into the common names because I test you on the common names because we use them a lot in class during the labs, but that's not something that we get to experience right now. And then the last rule, okay, the diatomic molecules do not follow the rules. What are the diatomic molecules? These are molecules where it's two of the same atom. And I'm going to give you a rule right now, and it's called the 7-up rule, okay? And that's because they form a 7 on the periodic table. So we're starting at nitrogen, okay? And we're going nitrogen, oxygen, fluorine. We're going down to chlorine, bromine, and iodine. And see how it forms a 7, okay? All right. And it's 7 up because there's 7 total, but here there's only 6, right? So we got to go 7, and then up over to hydrogen. That's your 7th one. And what the rule is with these ones is that they are never, ever, ever found alone, okay? You will never find hydrogen, just one hydrogen, okay? It's going to look like this. It's hydrogen with your subscript 2, okay? That's the diatomic. They're always found in 2s. Oxygen, okay? Subscript 2. They're always found in 2s. You'll never find them just one atom by itself, okay? Nitrogen gas, fluorine gas, chlorine gas. They're always found as 2, okay? So that's what the diatomic molecules are. Diatomic, di meaning 2, is you got 2 of the same atoms forming a molecule, okay? You'll never find these guys on their own. All right, so now let's just go over some of the naming ones. So I'm going to give you an example. So N3P2. And it is exactly, there's no crisscross method like the ionic compounds. So don't try to, switch the numbers back. Whatever the subscript is, that is the prefix you're giving to that one. So in this case, we have nitrogen, and there's a 3 beside nitrogen, okay? So what is that? Well, it's tri-nitrogen, okay? There's no crissing cross back and forth, so the 3 doesn't belong to the phosphorus, all right? There was no charges for these guys. It's just straight up, this is telling you that there is 3 nitrogen in this molecule, and there's 2 phosphorus, okay? So the next one is di. And we got to keep that same rule with the "-ide on the end. So trinitrogen diphosphide. Okay? Same goes for when it's giving you the name and you have to write the chemical formula. Alright, so let's go with disulfur. Again, pH or F, it doesn't matter. And tetrachloride. Okay, so the nice thing is it's giving you the subscript. So sulfur, well, it's telling you that there's 2. Awesome. Chlorine here, there's telling you that it's 4. Done. Okay, the naming from the chemical formula is so much easier because you don't have to try to figure out what the charges were. The prefixes tell you exactly how many of each of those atoms is in that molecule. All right, so you're going to go and you're going to do a bunch of those practice questions, the worksheet I gave you, and then I will take up a bunch of those ones tomorrow. And again, if you have any questions, pop onto the Google Meet and ask me.